The next topic that you're going to talk about is going to be EIGRP. Now, EIGRP is or used to be Cisco's proprietary routing protocol. They used to say that this was a hybrid routing protocol because according to Cisco marketing, it brought the best out of distance vector routing protocols and the best from link state routing protocols. But after being reminded repeatedly how bad that description for EIGRP is, these days it is called by its proper name, or it's categorized properly as an advanced distance vector routing protocol. Now, what advanced distance vector means is it still behaves in a very, very distance vector behavior. That means that it tries to use the same methods for loop prevention, which is for loop prevention, it is going to be using things like split horizon. It is going to be using count to infinity. And route poisoning. For example, now, this it might not actually be used, but these are the methods that distance vector routing protocols use for loop prevention. It is also going to be suffering from the same shortcomings that other distance vector protocols, well, namely RIP, suffers, which is limited visibility into the network. Basically, distance vector routing protocols know only those things that neighbor tell them about the networks. It's equivalent of me telling you, okay, if you are driving from New York to Los Angeles at the next intersection, turn right, and 537 intersections away, you will reach Los Angeles. Now, that tells you nothing, right? It tells you that, yeah, at the next intersection I have to turn left or right, but it doesn't tell you how far away the LA is, it doesn't tell you what the conditions on the road are, it doesn't tell you are there any tigers on the road or anything of the sort. It basically tells you, okay, at the next intersection, turn left or turn right. So that's what distance vector routing protocols are. Now, on the other hand, link state routing protocols, ISIS and OSPF, actually have much deeper understanding of the network. They can actually see the network of the whole roads. They know how distant things are. They know what the conditions are, how many hops away, and they know much, much more about the network. But both EIGRP and RIP, they basically know only up one hop away what happens. But this is where similarities between RIP and EIGRP actually end, and that's one of the reasons why Cisco for a very, very long time called it a hybrid routing protocol, because EIGRP will form neighbors, so it will form, so let's say that these are not shortcomings, but let's say that these are advantages over RIP as another distance vector routing protocol, is that the neighbors need to be adjacent. So we have neighbor adjacencies. We have dual algorithm for choosing the best paths and choosing the backup path. So it's very, very fast. And the timers, and it's very, very quick. I have to give it that. So it's even faster than OSPF. So EIGRP is an incredibly fast routing protocol. And more importantly, or I would maybe even say the most importantly, one of the major reasons why someone would choose to run EIGRP would be the ability to do unequal cost load balancing. So these are some of the advantages of EIGRP over RIP and possibly over other routing protocols, especially unequal cost load balancing. This puts it in a league ahead of OSPF and ahead of ISIS in many, many cases. Well, of course, the drawback is that, well, it is Cisco proprietary. it's Cisco only. I mean, of other vendors that I know of that actually support and implement EIGRP, only one comes to mind, and it's Alcatel-Lucent in very limited set of their equipment, and their implementation is a little bit shaky. Now that EIGRP has actually been standardized and RFC is published, we might see some multi-vendor implementations of EIGRP, but that standardization of EIGRP was done in such a way that interesting features from EIGRP, like, for example, the stub functionality is not documented. Well, it's not standardized, so it still remains Cisco proprietary. So it's really of limited use for everyone else to implement EIGRP, especially in 2013 when the whole world in a routed space is moving either to BGP or OSPF-based solutions. Now, there are some cases in which EIGRP makes a little bit more sense, like, for example, large DMVPN implementations. OSPF can suffer in those implementations. EIGRP fares a little bit better, but still, I mean, why run either one when you have perfectly alive and kicking BGP? But I digress here. So these are the things about EIGRP. Now, one of the things about EIGRP that makes it so great is the EIGRP metric. So EIGRP metric is actually rather interesting and complex topic, because there are actually 6 metrics that EIGRP uses. Now, I would like to say that these are not K values, because I have heard many times from students, EIGRP metrics are actually K values. K values are something completely different. They are not metrics. The 6 metrics of EIGRP are bandwidth, delay, reliability, load, and then we have MTU, we have 1, 2, 3, 4, 5, and hop count. Now, these 6 form something that EIGRP calls vector metric. And these are the values that are actually communicated in routing updates. Now, based on your configuration of K values, bandwidth, delay, reliability, and load will be used to calculate something that is called composite metric. So this is based on K values. Now, MTU here is used as the tiebreaker, and I will explain that a little bit later on. And hop count is the last resort loop prevention. And as you can see, MTU and hop count are not actually taken into account for the composite metric. To make things even more interesting, by default, EIGRP uses only bandwidth and delay for calculating the composite metric, but you can also specify to use reliability and load. But they also have very different behavior. Now, this is not something that you will find in any books or the training material, but I personally like to call bandwidth and delay hard metrics, and I like to call reliability and load soft metrics. Now, why do I call them hard and soft? If you have an interface that is enabled for EIGRP, it will actually have these 4 parameters. It will have the configured bandwidth, it will have the configured delay, it will have measured reliability and measured load. Now, reliability is the factor of how many errors you have on that interface, and this is how the value from 1 to 255 will be measured. And also the load, how loaded is the interface, what is the utilization of the interface on a scale from 1 to 255. Now, reliability and load are measured values, and bandwidth and delay are actually not measured, they are configured values. Now, any change in hard metric on an interface will cause the router, the EIGRP process on the router, to re-advertise the route associated with the interface. any change in soft metrics will not cause a reconvergence event, which means if a reliability changes or the load changes, the route will not be advertised. But if you change the bandwidth or if you change the delay on the interface, you are actually going to cause the router to re-advertise the route. Now, when a reconvergence event happens, and a reconvergence event is either the change in hard metrics or interface going up and down, the current snapshot value of reliability and load will be taken and put into the routing update and sent. So change in the soft metric does not trigger the reconvergence event, only the change in hard metrics. So this is how the EIGRP metric looks from the perspective of EIGRP database, or the topology table as it's called there. Now, based on these four values and the configured value of K values, and we have K1 to K5, the default being 10100. So these are the values for K1 through 5. We are going to be using EIGRP bandwidth, actually metric formula to calculate the actual EIGRP metric. Now, I know that you now expect me to actually write this formula here, but you are expecting a little bit too much of me. I don't think that no living human can actually remember this formula, and I am not even going to try to do that, but what I can do is I can tell you where to find it. So you can go to the Cisco documentation, you can navigate to iOS, navigate to any version of the iOS, go to the command references. In the command references, find IP routing protocols. In IP routing protocols, choose EIGRP and find the command reference for the command that is called metric weights. Now, when you find the command, when you find this command, if you scroll a little bit down, you will actually find what the EIGRP metric formula is, and there you will see how these values here for bandwidth, delay, reliability, and load, in combination with the K values, are used. So K values are basically just multiplying or are used to divide some of these values to come up with the value that we call EIGRP metric, the composite metric, which is just really a big number. Now, these values here are not all the same. So let's say that we have a network path. Let me be a little bit cleaner with this. So let's say that we have a network path that consists of several routers. And let's say that here we have some network N that gets advertised in this direction. So these are all EIGRP routers. So router 1 is actually injecting this route and it's advertising it this way. So each of these interfaces on the way, so these interfaces here, the outgoing interfaces, are not relevant for calculating the metric. It's only these interfaces here. So each of these interfaces here and this one here will have some value for bandwidth, some value for delay, some bandwidth for some value for reliability, some value for load, some value for MTU. Now, hop count is easy enough to determine. So let's see which value of bandwidth will actually be in use. So let's say that the bandwidth here was 1500, that bandwidth here was 10,000, that bandwidth here was 20,000, and the bandwidth here was 768. The value that we are going to end up using for bandwidth will be 768. Why? Because we are going to be using the lowest value of these values here to calculate what is our bandwidth in the routing update when it arrives on R4. So this is our observation point. So we are observing at this point. Now, for the delay, each of these interfaces will have some configured delay. So maybe it's 10,000 here, maybe it's 5,000 here. So maybe it's 5,000 here as well. And let's say that it is 10,000 here. So the actual value for the delay in this case will be 10,000 plus 5,000 plus 5,000 plus 10,000, which in our case would come up to, my math gives up 10, 20, 25, 30,000. So it will be the actual cumulative value of the bandwidth. So it's going to be sum of all delays on the interface. For reliability, spare me the time from giving you the values. It will be the lowest reliability. Why? Because how reliable is our end-to-end path? Our end-to-end path is as reliable as the least reliable link in the path. Also for load, how loaded is our path? Our path is as loaded as the most loaded link. So for the load, we are actually going to be carrying the highest value. For MTU, again, we are going to be carrying the lowest value. Why the lowest value? Because how big of a packet can we send on end-to-end path? Well, we can send the packet that is the size of the smallest MTU on the path. If the smallest MTU is 1500 and all other are 9000, can I send a 9000 bytes packet without fragmentation? I cannot. Therefore, EIGRP is going to inform the routers that, okay, the largest packet that can go on this path is 1500 bytes. So the lowest value of MTU is going to be carried. The hop count is cumulative. And by the way, the maximum by default, I'm just going to write this here, is 100. So EIGRP will not accept the route that has hop count that is higher than 100. This can be changed in the router EIGRP process, and the command for that is metric maximum hop count, or just metric hop count, something like that. I will show you this when we go into the command line. So this is how the values are carried across. So it's very, very important to understand how these values here function. These are the values that will be communicated in these routing updates. Now, what I'm going to do now is that I have explained how it actually works. I'm going to start simplifying it a little bit, because you know that these values are communicated, that the composite metric is calculated, and so on and so on. One of the very important things about EIGRP is EIGRP's ability to choose backup routes. Now, to talk about backup routes, I actually have to talk about something else first, which is, and this is a terrible subject, which is EIGRP terminology. And I think that Cisco should have a certification that deals only with this. So these are the things like successor, feasible successor, distance, feasible distance, advertised distance. Now, I'm going to put this in a table here, and I'm going to give this table a titles. So this is EIGRP, and this here is Common English. Okay. Now, what successor is really the best route, or I should say the best path to route. So if we have multiple possible destinations for a route, so let's say that we have our R5 here, and we have R2, and we have R4, and let's say that they're both advertising the same network here, and let's say that the route here has cost or metric of 5,000, and this one here has metric of 10,000. Basically, this one here is going to be called successor. Why? Because it's the best path to reach this network N that was advertised by both R2 and R4. So this is what a successor is. Now, feasible successor is the second best route. I should say second best loop-free route. Now, technically speaking, this is going to be the route that has passed something that is called feasible condition. feasible condition is a situation in which, and this is a chicken and the egg situation, feasible condition is a situation in which a route's advertised distance is lower than successor's distance. I say this is a chicken and the egg situation because here in the list I have the translations for advertised distance and the distance itself. Now, distance in the context of EIGRP is simply metric. Or I should say, calculated metric. Now, feasible distance is successor's metric. So, small correction here. This is feasible distance. So, let me just quickly do one thing. Let me divide these so that you know which one is dealing with what. Now, advertised distance is the metric as advertised by the neighbor. Okay, so this is the translation between EIGRP and the Common English. Now, let's see it in an example. So, again, I'm going to use the example of my R2 connected to R5, connected to R4. Now, let's say that it's only R2 here advertising a certain route. So there is a route N here, and R2 is injecting this into EIGRP and is advertising this route towards R5. Now, R5 here is receiving this routing update, and this routing update says that network N is reachable via R2 and there is certain metric. So let's say that this is some metric. Now, this value here from R5, so we are observing from here, so this is our observation point. This metric here, as advertised by R2, is advertised distance. Now, R5 is going to take this route and it's going to go through the bandwidth, reliability, delay, load, whatever else it needs to do, and it's going to calculate and inject in its routing table route network N through R2 with metric X. Now, this metric X from R2's perspective is what we call feasible distance. So this is the best route, and this here, this route as injected into the routing table from R5's perspective is called successor. Now, let's say that R4 here is also advertising this route, but with slightly worse metric. And let's say here that this metric here is metric Z. So let's say that this was metric Y here. So this again, from R5's perspective, this metric is advertised distance. But now we have two routes that we are receiving. We have this route here that is advertised by R2, and we have this route here that is advertised by R4. Now, I said that R2 is better route, so let me just say that this one is better, and this one here is worse. It doesn't matter, the actual values don't matter. So now, what R5 is going to look for is this value here, lower than this value here? So this value and this value here will be compared, and if z is, or z for you over the pond, if z is lower than x, then we say that feasible condition exists, and this route here, as it was advertised, after it was computed and munched, comes here as the backup route. So this is the second best route, and it's loop free. We say that this route now is a feasible successor. Now, how can we tell that this route is loop free? Well, that's precisely what this does. This bit here determines if the route is loop free. So this is exactly what feasible condition does. Shouldn't z or z be higher value than x? Well, no. And let me explain. So for that, I'm going to use a slightly different example. Let's say that we have a network that looks like this. So we have R1 that is connected to R2, that is connected to R3, that is then connected to R4, that is then connected to R2. Now, let's see that R1 now advertises the route to R2. Now, I'm, for whatever reason, going to completely ignore the fact that R2 is going to advertise this route to R4. So let's say that this is filtered out for whatever reason, okay? Because by default it will be advertised there, but let's just pretend it's not advertised. And in EIGRP it's a perfectly valid scenario because it could have been filtered out. So this route here becomes a successor, and it has metric x. Now, when this route actually gets advertised to R3, the metric here is going to be x plus something. Now, when this route gets advertised here, it will be x plus n plus something. Now, when this route gets advertised here, it will be x plus n plus n plus something, right? So this value here is now higher than this value here. Now, if this value is higher than this value here, we have a situation in which a loop condition might exist. Okay, so the advertised route, or actually, I'm sorry, just 1 second. I messed this example up. So let me retry because I understand it, because I know exactly what I was thinking, but when you look at this slide later on, it may not be entirely clear what I had in mind. So let me try to do this again. So this is the successor's distance, right? So this is what's going to be the advertised distance of this route is actually going to be x at this point. Now, the advertised, and let's say that the cost of this interface is n. The advertised distance at this point is going to be x plus n. Now, let's say that this cost here was also some n. The advertised distance at this point here will be x plus n, so basically this value here, plus my own cost of n. Make sense? So now this route here arrives at this point, and we are looking at this advertised distance of this route. Now, if this value is higher than this value, that means that it is theoretically possible that this was our own route. And in this case, it was our own route from R2's perspective. This was the route advertised by R1, So we have our own cost, we are advertising to R3, R3 is advertising it to R4, and R4 is advertising it back to us. So at this point, by just looking at this value, so there is no feasibility condition here. So feasibility condition does not exist. Why? Because we cannot guarantee, not guaranteed to be loop free. Now, in this example, it's obvious this is a loop. Now, keep in mind, what is R2's perspective of the network? Now, this is what R2 sees. Remember, this is a distance vector routing protocol. This is R2's view of the world. This is the only thing that R2 knows about. It knows that it's connected to R1, that it's connected to R3, and that it's connected to R4. It has no idea that this connection here exists, what are the advertised distances here, what are the metrics. It has no idea. It only has the information that R3 and R3 and R4 are actually telling it. So this is the problem. So the only thing that we have to go on is this information here. But let's take a look at this. So another example, very similar to this one. Again, we are going to have R1, we are going to have R2, and we are going to have R4 here. And let's say that we have R3. So now we have this situation here. As I said, very similar example. Now, let's say that the route gets advertised here, and the calculated metric, so successor distance, is, let's say, X. This route gets advertised here, irrelevant. I'm going to ignore the fact that this route is being advertised to R4, but I'm not going to ignore the fact that this route is being advertised here. So at this point, this is going to be some metric. Let's give it metric, let's say, Y. So at this point, this is a successor on R4. So R4 advertises this route as Y. And let's say here that Y is actually lower than X. Now, there is some cost on this interface here, let's say some value Z. So when this actually gets calculated, I'm going to have that Y plus Z actually is higher than X. So this one here does not become a successor. So this is the second best route. But what we are going to look at is actually this value here, Y, and we can tell that Y is actually lower than our own metric, which means that this is a guaranteed loop-free route. Why is it guaranteed loop-free? Because the assumption here is that when we advertise route to our neighbor, that neighbor can only increase the cost. It can never decrease the cost. And this is true. With EIGRP, you can never decrease the cost. You can only increase the cost of the route. You can, there is a configuration where the route will remain of the same cost. This is why it's important to understand that this value here, the feasibility condition, is actually feasible distance needs to be higher, or actually feasible distance needs to be higher than the advertised distance of the route, not higher and equal. So not higher and equal. It actually needs to be higher than the advertised distance for a feasibility condition to succeed. So in this case here, this is true. Our low value Y, the advertised distance, is lower than the feasible distance. So if we turn this around, the feasible distance is actually higher than the advertised distance. We say that here the feasibility condition does exist, and this second best route becomes a feasible successor. This is an incredibly important concept. Why is this incredibly important concept? Because if we have a feasible successor, in our network. So if we do have a feasible successor, that is the second best route that can be immediately promoted to be a successor, should successor disappear. So what I mean by disappear, let's say that the best route disappears from the routing table, the interface somewhere went down, or we lost that neighbor. If we have a feasible successor, the router can independently from all other routers just say, okay, this is the second best route, it's loop free. Now, in this case here, when we actually did have a loop, now this second best route that R2 received cannot be immediately promoted. So what needs to happen in that case? So let me just make a copy of this page. So what needs to happen here on R2 if this route actually disappears from the routing table? So if we lose this route here, the router cannot simply promote this route because we have not passed the feasible condition. What R2 needs to do is actually it needs to send out the query asking R4, hey, do you still have this route? Basically what R2 needs to do is what we say, it needs to go active on the route. Now when the interface, when the route goes active, basically R2 has sent a question to R4 and now waits. It cannot use this route because R4 now needs to verify, okay, what's my best route? I'm receiving the query from the neighbor. Is this my local route? No. So basically what it needs to do is forward the query here to R3 asking it, hey, that route you have, is it still good? And R3 now sends it to R2. Hey, is this route still good? And what does R2 say? Well, no, I don't have this route. So R3 now says, hey, I don't have the route, removes it from the routing table, sends it to R4, informing it, hey, this route is no good. And this information goes back to R2, hey, this route is no good. So basically, we now prevent the looped route from going into the routing table back on R2. So this is what needs to happen when when the successor disappears and we don't have a feasible condition. Now, in this situation here, where we actually did have a feasible condition, so let me make a copy of this slide here. What's going to happen here? Let's say that R2 has lost this route. So this route has disappeared from the routing table. Now, what R2 does, hey, I actually have a feasible successor. This route has disappeared. This now, bam, gets promoted to be successor without the route actually going active in this case. Now, what would happen if this route here actually wasn't a feasible successor? So if this wasn't true, we still have the same network setup, but let's say that this value here of the advertised route, so this advertised route, so Y is actually higher than X. So this now does not pass a feasibility condition on R2. So this is a second best route, but it's not a feasible successor. Now, we know for a fact that this is a loop-free environment, but remember, R2 doesn't know that. The R2 has only this information to go on, and it has determined that it cannot guarantee that this is a loop-free route. It might or might not be, but it cannot guarantee. So when this route disappears from the routing table, what R2 is going to do is it's going to go active on the route. R4 is going to send this information to R1, and R1 is going to say, yeah, you know what, yeah, this is a valid route, you can still use it. Sends back information to R4, and R4 sends back information to R2 telling it, hey, yeah, this route is valid. So what happens at this point? The second best route becomes a successor. But in this case, R2 couldn't make its own determination about it. It actually needed to ask about it. It needed to go through this active process about it. Now, when the route goes active, when this happens, there is an inherent danger that something along the way is going to get stuck. Let's say, for example, that there was a particularly weird communication problem on this link, where the traffic would, for example, go to R1, but EIGRP responses were being dropped at this point here. That means that this router here has went active on the route and is waiting. This router here has went active on the route and is waiting. Now, there is a timeout for this. In the early days of EIGRP, actually until relatively recently, a couple of years ago, this was actually a very, very dangerous situation which was called stuck inactive, SIA. Now, what happens in SIA is that router R2, when it doesn't receive the response from R4, and by the way, the relationship between R2 and R4 is perfectly fine, it is actually going to say, hey, you know what, I'm stuck inactive, I have been waiting for your response, you're not responding, so I'm going to tear down the adjacency with you. R4 is going to do the same thing here, but the damage has been done. Imagine other networks that were behind R4 and R2. They just lost the communication because there was a problem between R1 and R4. Everything was okay between R2 and R4, but there was a problem between R1 and R4. So what is happening at this point on R4 is, and R2, they are going to re-establish adjacency because there is a problem here. This adjacency doesn't re-establish, but there was a damage done at this point. This is why relatively recently in the iOS there has been an introduction of stuck inactive query. The way it works is when R2 at this point sent query, and when the timeout happens, it actually sends out stuck inactive query. It asks R4, hey, are you maybe waiting on response yourself? But are we okay? Is everything okay between the two of us? R4 says, yeah, I'm waiting for response, but we are good. Now R4 is going to do the same thing. Hey, are you maybe waiting for response? And R1 may or may not respond, but then R4 knows that this is where the problem is and tears down this adjacency, right? So this adjacency is going to go down, but this adjacency between R2 and R4 actually stays in place. Load sharing in EIGRP comes in two flavors. One is ECMP, or equal cost multipath, and the other one is unequal cost multipath. Now I just invented this, so this is my invention, and this is unequal cost load sharing. Now ECMP here is relatively standardized name for also something that is simply called equal cost load sharing. Of course, you know that sometimes sharing is also called balancing, but I personally dislike using that term. Now, I say it comes in two flavors because they are configured in very, very different ways. Now, this here is done by default. So this is what iOS does by default for every single protocol, well, except for BGP where you need to explicitly configure it, but for all IGPs, for static routes, for anything, equal cost multipath is implemented by default and there's nothing you need to do to make it happen. So for equal cost load sharing, what you need to do is if you have two paths, must have equal cost. That's it. This is what you need to satisfy in order to implement equal cost multipath or load sharing. So if we have, let's say, R1 that has connections to R2 and R3, and R2 and R3 are advertising the same network here to R1, if these are the same metric, and these interfaces are the same, basically what's going to end up in the routing table here are two routes. There is nothing you need to do to make this happen. And we have actually seen it today multiple times, because multiple times in my network I have actually done this. I had multiple paths and 2 routes showed up. So this is equal cost load sharing. Now, the reason why I went through this explanation here is for you to understand that in the lab, if they tell you perform equal cost load sharing between path A and path B, there is only one way to make that happen, and that is to make sure that 2 paths have equal cost. If they don't have the equal cost, you will not have equal cost load sharing. So there is only one way to make that happen. Now, there are multiple ways how you can make this cost the same, right? So I'm not saying that there is only one way to actually implement this, but there is only the only one way you can meet the conditions that are required to have equal cost load sharing. That is that 2 paths for the same destination have the exact same calculated cost. Now, this is true for OSPF, this is true for EIGRP, this is true for RIP. But the danger there is that in the lab, they might put you in a position that they say something along these lines. Let's say that you have R1 that has connection to R2 and R3. Now, the connection between R1 and R2, let's say that this is a gigabit interface, and let's say that this here is fast Ethernet interface. Now, they're going to tell you, perform equal cost load balancing to network N through R2 and R3 from R1 in this case. And in almost 100% of the cases, when I have this in one of my 1-week lab experience labs, in 100% cases, what students do here, they would go to router, EIGRP here, and they would say variance X, whatever the X is. Now, this is incorrect. This is incorrect because this is not the way to solve this task. The task here called for equal cost. What you need to do is make sure that cost here and here is the same cost. This is what you need to do. So what you need to do is either change bandwidth, change delay, or use offset list to change metric, right? Now, if you go the variance way, you are actually configuring unequal cost. So unequal cost So for unequal cost load sharing, this is where you are going to be using router EIGRP, and you will be using variance X. Now, let me explain how this works. So what variance X is going to do? Variance multiplies distance of the successor route by the value specified, or I should say with the value. English, not my first language, apologies. Or maybe it is by, but it doesn't matter. Variance multiplies distance of the successor with the value of variance. All routes that have already passed the feasibility condition, and here, even though this implies it, I'm going to say before multiplication, and have distance lower or equal to feasible distance multiplied by variance will be inserted into rib end. Let me explain this. So variance, so when you specify variance x, you're going to have a successor route, the best route. Now, before that multiplication has happened, some routes have passed a feasibility condition. So one of them is considered to be a feasible successor. Some of them are not feasible successors, but they have still passed the feasibility conditions. Now, you might have routes that have not passed the feasibility conditions, and those are ineligible for load sharing. So only those that have already passed the feasibility condition are going to be eligible for load sharing. So those routes that have already passed the feasibility condition before the multiplication has happened are now going to be considered for load balancing. So now we are taking a look at the distance of the successor multiplied by the variance, and all those routes that have passed the feasibility condition that have their own distance lower or equal, so in this case lower or equal actually is okay, unlike feasibility condition, are going to be inserted into the routing table. So what you might end up having in a routing table is successor that has the cost 1,000, and then you might have a feasible successor that now has cost 2,000, and you may have other route that has the route 3,000. So from this we can, and let's say the route that didn't make the cut had the cost of 4,000. So here we can deduce that the variance was very likely 3. Why? Because we looked at the routes, and let's say that they passed the feasibility condition. So these two passed the feasibility condition, and this route here did not. So if we multiply variance 3, we are considering only these two routes here. So they have already passed the feasibility condition, and then we multiply this by 3. So the new value for comparison is 3,000. So all the routes that have passed the feasibility condition that have their own cost at 3,000 or less are going to be inserted into the routing table. So these two end up in the routing table. Now, the traffic is actually going to be sent across these 3 routes in, I'm guessing this, I'm probably going to get it wrong. It can actually be calculated, and on our blog there is actually an instruction how to do that. But probably, so if the costs are 1,000, 2,000, 3,000, the most likely traffic distribution here will be 3, 2, 1. So we're going to send 3 packets this way, 2 packets this way, and 1 packet this way. And of course, because iOS doesn't implement per packet load sharing by default, it implements per destination. This may not be scientifically correct, but 3 destinations will use this path, 2 destinations will use this path, and 1 destination will use this path. So the actual traffic distribution will follow some, will be sent according to the ratio of the original metrics that were in use. Of course, it is not as simple as this, but I said I will be simplifying things a little bit. You don't really need to know this in great detail. You just need to know that this kind of behavior will actually happen. Important thing that I want to talk about EIGRP is the offset list. Now, offset list, and I mentioned it a couple of times today, is a very, very simple way to actually influence the metric of EIGRP route. Now, what I mean by influence the metric of EIGRP route is basically increase the cost. We cannot decrease the cost, but we can increase the metric of the route. Now, the good thing about the offset list is that it actually works with calculated cost. So, for example, if we had a situation that we had R1 that is advertising some route to R2, and the task says, make sure that this route is in a routing table with the exact cost of 3 million, we could easily do this thing. So let me show you this on an example. So here on R2, R4, R5, I'm quickly going to configure EIGRP. So I'm just going to remove the RIP configuration, and I'm going to add EIGRP config. So EIGRP, let's say 254, no auto summary, network all zeros. So this is going to be the configuration on R2, R5, and R4. And let me remove that static route because I will forget about it. So now if I take a look at R5, show IP route, EIGRP, I'm seeing, let's say, this 224,000 route. Now it has the cost of 2,297,856. And let's say that the task says, make sure that you have this route in the routing table from both of these routers with the exact cost of 3 million. Well, that is something that we can easily solve. Oops, sorry about that. That we can easily solve. So I'm just going to bring in the calculator here. So I'm going to say 3 million minus this value, and this is how much I actually have to increase my cost by. So what I'm going to do now is I'm going to go to my router EIGRP. Actually, let me do it in the command line. So here, router EIGRP 254, I'm going to say offset list, and here I can either specify an access list or I can specify 0. If I say 0, it applies to all the routes. That's exactly what I want. And I want this to happen in the inbound direction. And how much do I want to offset my routes? And the number there was 702.144. So 702.144. And I want this to happen on all the interfaces, but I can also specify it on a particular interface. So when I do this, what's going to happen is it is going to take some time. The router actually needs to reset to resync the neighbor relationships, which just happened. So if I do show IP route EIGRP, here they are. Both of my routes are in the routing table with the exact cost of 3 million. So this offset list looks like a magic bullet. Well, as you know, there is no such thing. And offset list is not a magic bullet. Now, why is it not a magic bullet? Because remember, EIGRP uses something that is called vector metric, which means that the calculated value is never actually communicated to any of the neighbors. So when you use the offset list, you are actually influencing calculated metric, which means that you are influencing a composite metric. And if composite metric is never communicated to any of your peers, does this mean that offset list influences only the local device? Well, let's take a look at that as well. So here I have increased the cost on my routes significantly. So if I do show IP route EIGRP, let's take a look at, let's add one more route on R2. So interface loopback 0, I'm going to say IP address 2222/32. So now take a look at the cost of 2222 on R4. The cost is 3,512,000. So I'm going to go to R5 in the router EIGRP, and I'm going to remove the offset list from the configuration. So now I need to be patient for a couple of seconds until the routers actually resync, and that should be happening anytime now, or I'm going to obsessively started pressing enter, that's good. So now I'm going to say show IP route EIGRP and take a look at the route now. So when I have removed the offset list, the metric is 2.8 million and here was 3.5 million. And the difference between this value and this value here, you can guess it, is going to be 702,144. So the exact number that I have increased my metric by. So knowing that the composite metric is never communicated to the neighbors, how did this actually work? How did my change on R5 get propagated to R4? Well, for that we have to dig a little bit deeper. So what I'm going to do now is going to go back to my terminal and I'm going to, on R4, take a look at the topology table. So show IP EIGRP topology table and I'm looking at this route here. So this is my vector metric. Here I see the composite metric. This is the local value. This is the advertised distance learned from R5 and this is the calculated local admin distance. So this here is the vector metric. So I'm just going to add a delimiter here and let's add back the offset list. Again, we're going to wait for the resync. Actually, you know what? I'm going to actually copy this to a text editor. So this was before change. Now let's see after change. Take a look at this. So this is the new vector metric. So I'm going to copy it and let's paste it here. Take a look at this value. This was before change. This was after change. This is the delay. So offset list actually modifies the delay. And this is actually very significant. Because imagine that you had in your lab a task that says, make sure that router R1 is preferring this path over this path, and by the way, do not modify delay in any way. And you're thinking, oh yeah, that's cool, I'll just use the offset list. Well, how did that go? Why did you lose points on that particular task? Well, because you used the offset list. You have modified the delay. Now, be careful there, because the task would say, make sure that router is preferring this path over this path, but do not modify delay on any interface. Now, in that case, using offset list is a perfectly fine thing to do, because you're not actually changing the delay on any interface. You're changing the delay for a particular route or subset of routes. But it's important to understand that offset list modifies the delay. Now, this is also important to know, especially if in your lab, I'm just going to add always modifies the delay. If in your lab they told you, do not take delay into account when calculating the metric. So you are smart, you go and type in metric weights and you eliminate the delay, so basically just 100000. And what happens then, you have a traffic engineering task that says, oh, send the routes this way, not that way, use the offset list, and it has no effect. Well, it did have the effect. What offset list did in that case was it will modify the delay, right? So this would still happen even if you're not taking delay into account. But what is not going to change is the calculated composite metric, because this value, when calculating the composite metric, is going to be ignored. So offset list will always modify just the delay. So it's not a magic bullet. You have to know how it works and you have to know how to use it and when to use it.